where were we? We were in.
Can I ask something about the single cycle processor before we start?
Yeah, go ahead.
So into the control, the bits 26 to 31 go in there, right? If I decide to also put bits from 0 to 10 in there, and I want the control to recognize if from 0 to 10 it's all zeros, and if from bit 26 to 31 it's 23, and then it will recognize it's this instruction. Can I just say that?
Then you have to rebuild the controller.
What do you mean exactly?
Well, that's a good question. I mean, normally, which bits did you say you want to put in? Which bits did you say you want to put in?
I want to, it's actually for question 2 of homework 3. I want to put, it was the question where you have
I'm just curious which bits, which number bits.
from 0 to 10 I want to put in there, and from 26 to 31.
Well, 26, 31 were always there. You want to add 0
true.
to 10.
So I would add 0, 10, and if they are all zeros, it would recognize this new instruction. Like a legal thing to say?
Well, why do you want to do that? Why not just, I mean, is it affecting those bits, all those bits you need to be 0? It's the only way you can tell that it's this command that you want to do?
Because load word, we're using load word, but I don't want it to recognize that it's load word, because it's not load word what we're doing. I want it to recognize that we're adding 2 registers into 1. So
why are you not allowed to change the opcode?
Am I allowed to change the opcode for this? Because it says we're using load word, but then just changing with 3 registers instead of the actual load word. Changing the opcode, then it's easy. Then I just change it into a new number, and I don't need to change the control unit at all.
I mean, the control unit will go through various changes, actually. Right, you have to specify the changes that now the control unit does. It now behaves differently. I'm just saying, which Targil is this? This is homework 2 or 3?
Homework 3, question 2. Basically what I thought, this is just my set, since we're using 3 registers, which are all just 5 bits, those are 15 bits, and then the command is 6 bits, then we have 11 bit or 10 bits that are not doing anything.
Wait a second. I'm zooming here. Let me share my screen. You're talking about these questions here? Question 3?
Question 2. Question 2. Yes.
No, the command is neither in the R format or the I format because it contains 3 registers. So it also accesses the memory. This means we must change the controller to recognize this new format. So yes, you're going to change the controller.
That's why I thought to put in bits 0 to 10 in there, and if they're all 0, it would recognize this format because we're not using those anyway.
I don't see the need for that. Why don't you just make up make a number that's not being used?
So I can just say load word, this thing is not 23, it is whatever number is not used.
Well, you got to, yes, exactly. This is a different load word, and it has a different opcode. Because remember, only the R type uses the, as everything that's not an R type, everything, then you know immediately from the opcode what it is. So the simplest thing to do is just to find an opcode that's not in use and use that one for this command. The fact that it's a load word, it's obviously shouldn't have the same opcode as the regular load word because it's a different command. How would it know? It must have a different, the 00 is not going to help you. It must have a different opcode. Because if it wouldn't have a different opcode, if it would be the same opcode as a normal load word, then it would come and look at this thing and think it's part of the address. Right, RS, RT, the RD would be part of the offset. And it would not know, and it wouldn't care about those zeros that you put there. Put as many zeros as you want. It's going to think it's part of the offset. It's going to combine the RD with the offset with those zeros that you put in there, and it's going to misconstrue that as the offset.
Well,
because it thinks it's a regular load word.
We want to give it a new...
ARD registers 5 bits, so each of those registers are 5 bits. So in total, LW, RD, RS, RT are together 21 bits. So we have 11 bits that are 0.
Everything you said is 100% true, but it's irrelevant. Because this is the opcode, this is the RS, this is the RT. That's the first 16 bits. If the opcode says it's an LW, it's going to look at the next 16 bits, which includes the RD and your zeros, as the offset. How should it know that it's not supposed to do that? It sees that this is an opcode for a load word.
Okay.
So therefore, the only solution is that the opcode will be different. You understand what I'm saying?
Yes, thank you.
Yeah, okay.
In part C, it's asking about every other instruction. So are you supposed to go through every instruction, or you're just supposed to say it's supposed to be off for every other instruction?
Well, if it's off for every other instruction, then you've answered the question. Yeah. You don't have to say it's off for this one, it's off for that one.
I'm saying, is it feasible that that would not be the case, and then you'd have to go through every instruction and decide?
Yes, theoretically, that's the whole point. Yes, it is possible that, or let's say for all instructions, it's off except for this instruction. You know what I mean? It could be, yes. I mean, you don't have to list every single instruction. What you have to do is say it's true for all the other ones, it's like this, or for all the other ones except these two, it's this. But yeah, is it feasible? I mean, I don't, yes, it is theoretically, yes. Okay, I mean, unlikely, but yes, it is feasible. It's possible. I mean, in all the examples that we did, there was always, it was just not in use for those other commands. Fine. Let's go back to the lecture material. What do I want here? And so anyway, I uploaded, as I said before, I want you to all look at that. I uploaded a little 8-minute video of me by hand doing the Booth algorithm for a negative number and for 7 times -3, I think it is. Yeah, 7 times -3, the same example, and you'll see how it works out. So we concluded about speed measurements that they all have their flaws. And we even did this example. Is that right? Yes, do we remember doing this example?
Yeah, I think we finished on this.
Yes, we finished this, thank you. So, right, we talked about how the CC didn't change, and therefore the result of how many cycles was enough to tell us which one is better. Since this one did the same program in more cycles, it's obviously worse, took longer. But had the CC, had the cycle, the clock cycle, I don't like this name CC, it's very confusing because it really should be CCL, clock cycle length. It's a time. It's very important to understand that it's a time. It's the actual length of of each individual little tiny cycle. So if the cycles got shorter somehow in the new computer, if it's instead of a 1 gigahertz, it's a 4 gigahertz machine, then this can be a better computer. Even though it's more cycles, the cycles are shorter. So that's why you have to multiply that. In our case, the question had specified that the cycles don't change. So if the cycle speed doesn't change, if the length of time it doesn't change, then for sure the number of cycles is sufficient to know which computer will run the program faster. Okay, now we're in another type of problem, which is a very good type because it'll show you something that we explained before about it'll make some points clear. So given two computers with a clock frequency of 100 megahertz, so they're obviously some kind of old computer because now computers are gigahertz and they're so it's got a 100 megahertz computer running the same benchmark program written in a high level language. Remember, in a high level language. That's always how we're going to do things when we're talking about floating point. And with the following distribution of actions. Now, FP means floating point. So the program has 10% floating point multiplication, 15% floating point addition, 5% floating point division, and 70%, let's say for the sake of argument, everything else, but integer action. Actions with integers. That's our program. So that's the program. That is the benchmark program. That is the mix in the program, right? Every program has a different mix. That's the particular one we're testing with. And we're going to run it on these two different computers. We didn't yet explain. So far, we said what's in common between the two computers. They have the same speed, and they're running the same program. Now, what's the situation? The first computer is a MFP. I think M stands for like machine or something like that. It's a floating point machine. FP is floating point. I'm not sure exactly what M stands for, but it's just what he called it. It doesn't really matter. But it's a machine that does floating point, maybe a micro floating point. I don't know. If it would be Hebrew, I'd say machshev, but it's not Hebrew. It is a floating point computer, which means it's like an advanced computer. Just remember, think of it that way. It's the more advanced computer with a dedicated hardware to calculate floating point operations. Now, remember, we've gone through and explained about floating point operations and how they are complicated. They have lots and lots of steps. Obviously, this is something that can't be done in 5 clock cycles. You're going to have to do many, many shifts and many, many steps. So we might decide to build some extra hardware that has built into it some kind of shifts so that we can in one cycle or whatever, so that we could in a faster way, maybe not in 5 cycles, maybe in 10 cycles, but maybe in a faster way, we can get our floating point operations done in our hardware by building special hardware to deal with floating point arithmetic. The second computer is a NFP, a not, N is for not, I think, not machine floating point. In other words, it's a not floating point machine. It doesn't have special abilities to do floating point. It can do only integer operations. So it runs the program by means of emulation, meaning the compiler translates each floating point operation into several int operations. So wait a second, let's stop there. This is a point that we were talking about before, because you were asking me, how is it that, well, forget about what we were talking about before. Let's just say like this. What does it mean it doesn't do a floating point? I write in my C++ program, give me a float, give me another float, multiply them, give me the result. This computer has no ability to do floating point operations directly. So what does it do? It doesn't know anything about floating points. It just knows about integers. So the compiler has to work overtime. The compiler has to say, oh, in your upper level language, you wrote take two floats and multiply them, I'm going to turn that into a whole lot of commands in integer with integers that by the end of the day is going to give me the same result as the float operation that you wanted, and you're not going to know the difference. So I may take your one line of C++ and turn it into 60 lines of assembly, but those 60 lines of assembly will get you the result that you want. Will get you the floating point thing by doing a whole algorithm of commands like we learned, because we did floating point multiplication without actually multiplying, just by shifting and adding. So theoretically, I can make a computer that doesn't know anything about floating point, and it can just shift and add and do what it needs to do and get the result. Whereas the first computer the compiler didn't need to do any work. The compiler just said, it just went and found in the instruction set of that computer a particular command which is called multiply two floats, and it ran it. So the compiler could just directly translate the command from C++ into machine language in this machine, but in this machine, in the NMFP, it couldn't. So it had to work extra. Somebody who wrote the compiler, wrote a more complicated compiler, which had to deal with how do you convert, and that's what it means by emulation. Now it says here that each int operation takes 2 cycles. That's in the NFP. We're going to see now that there's some differences between the two. So look, we said already that the NMFP, every operation, and we can add a column here. Maybe I'll add a column here, because I added one. Insert column. I can't see what it says. Insert column right. And now wait just a second. And let's call this cycles per instruction. I'll fix that later. Cycles per instruction. Well, actually, no, I want to take that away. Let me undo this. Sorry. This may make it confusing. Okay. So
for the MFP, why do we need more cycles for the addition rather than the multiplication?
This is not cycles. That's what I was trying to say. It's not cycles. This is actually number of int operations. We could add in here. Here, this is
on the left side for the MFP.
For the MFP, a floating point operation takes 4 cycles.
But addition takes 6.
Yeah. You're asking me why? Because that's what the question. That's the given of the question. I can change this to 300, this to 12, this to 4,272. That's just the numbers. I don't care what the numbers are. That's just the question. The question says, this is what the reality is. You're asking me, why does it take this much rocket fuel to send a man to the moon? Because that's how much it takes. I don't know. Number, it's a question. Given that this plane travels at this speed, and this plane travels at that speed, and this plane travels at this other speed, then which one gets there first? I don't know. This is just telling me a given of the question. The given of the question is that the number of cycles for the floating point. Remember, this is a question. This is not, we're not teaching theory. We are teaching a question, example. This is an example question. So the given is that the number of cycles on the more powerful new machine is 4 for multiplication, 6 for addition, 20 for division, and 2 for integer. Now I added this column last class when I was teaching to another group, and I added this column because it's kind of dumb that I added it, but I added it because they were unclear about this. Number of instructions is a different thing from number of cycles. Number of instructions for a float is 1 instruction. Number of instructions for an addition is 1 instruction. This is a floating point addition. Number of instructions for a division is one instruction. Obviously, this is what it is. What about over here? In the non-advanced computer, so how many int operations, how many instructions? This is not the same as cycles. This is how many instructions. So it's 30 instructions to get through a multiplication done. In other words, I'm going to add here times 2 cycles, just to be clear. But this is in parentheses. This is not actually supposed to be written here. I'm just clarifying it for you now. We'll clarify it later. But you understand why I'm writing this? Does somebody understand why I'm writing this? Or does nobody understand why I'm writing this?
I don't get it.
I understand.
Okay, so we have someone understand, someone don't get it. So
Because it
That's
said
good.
in the thing that for each one it takes 2 cycles, no? To do it in
exactly, it said here on the non-NFP, every instruction is performed in 2 cycles. Whereas in it's kavua, it's fixed. It's always 2 cycles. But that's in the not advanced computer. Every integer instruction, this is number of integer operations that are executed for each FP operation, each floating point operation. In other words, if I want to do a floating point multiplication, I need to do 30 integer instructions. Now, each of those instructions itself is 2 cycles. Over here, I just am writing cycles. These are not the number of instructions. The number of instructions is 1. That's why these 2 charts are not comparing the same things. This is how many instructions I need to do to emulate a multiplication of a floating point. This is how many cycles I need to actually do a floating point, not to because that is 1 instruction. So that's the situation.
For the NMFP, it's not listed there, but it's for the NFP. But for integer operations, does it just take 1 cycle?
No. Can anybody else answer for you?
I don't remember what it said in the question.
Does somebody else remember? Nobody else remembers? Jump in. So it takes 2. It takes 2. I mean, I could add that. You're right. I could add a column here. But it's sort of obvious. I mean, it's supposed to be obvious.
Oh, sorry. I was not. I didn't read the chart correctly.
Yeah, it's very confusing because these 2 charts are not the same thing. I could add. This is the number of int operations that it takes. So it obviously takes 1 operation to do an int operation because that's what int operation is. I could write int operation, but this is, and then write 1 int operation to do an int operation. And then it would be times 2 cycles. But cycles would be 2. So now let's go to the next slide. Question. Calculate the million instructions per second for the 2 computers. Now remember, million instructions per second is how many million instructions I can do in a second. So your answer could be like, if for example, the instruction count of the program. This is like, let's say you have a program that has 1 million instructions in it. That's how many instructions are in that program. And the CPU time is, let's say, 1 second. What does it mean CPU time is 1 second? It took 1 second to do all those million instructions. So 1 million divided by 1, but multiplied by 1 million. So it's actually 1 million divided by 1 million, which is 1, divided by 1, which is 1. So we'll get 1 million instructions per second. Well, that makes a lot of sense because if this is 1 million instructions and it did it in a second, then it's obviously a MIPS of 1. 1 million.
Divide the denominator by 1,000,000 just because MIPS is counting per million.
Yes, MIPS is million instructions per second. It's not IPS. If it would be IPS, then we wouldn't divide it by 1,000,000.
Yeah.
But it's millions of instructions. So it's like if you ever saw in economics like a table of like how much IBM made in a given year, and it says 7,000, and then above in the table it says number in millions. So it didn't really make what did I say, 7 million? 7,000? Didn't make 7,000. It made 7,000 million, made 7 billion. But they just write it. The table is in millions because they're going to talk about IBM, how much they make in a year. Obviously, it's in the millions. So you just write 7,000, and then the table tells you that it's in millions. So this is in millions. How many millions of instructions it can do in a second? Because no computer can do less than 1,000,000 instructions in a second. So at least it can have 1,000,000. Maybe it'll be more. Maybe it'll be 7 million per second. Maybe 100 million. Maybe 1,000 million per second. A MIPS of 1,000 would be good. So that's why we divide it by 1,000, by 1,000,000. Again, the example, if it did 1,000,000 instructions and it did it in 1 second, then it would be 1,000,000 divided by 1,000,000 divided by 1 would be 1 million instructions per second. That exactly makes sense. Now, what we do over here on the right, let's look at that. Well, that says like this. Well, how did we get that? Yeah, that's an interesting question.
Well, I have a question. Why do we need this thing on the right? If they're all equal, then we can just choose one and do it, right? We don't need both of them.
Yes, that is true. We could use this one to get it, or we could use this one to get it.
I guess
Depends
it's
on
depending on which information we have.
What?
I guess it's depending on which information we have.
Yeah, it's basically just for convenience.
Okay.
All right, so yeah, so you're asking why this other equation here. And it's a good question. Right, we don't necessarily need it, but
could it technically be the CR divided by the CPU time times 1,000,000?
well, wait a second.
Can we mix and match?
Yeah, anything you can take anything that gives you the instruction count. Well, let's see. What is a CR? Let's go back and remind ourselves of what the CR is. It's just games. We're just playing games with numbers here. It's not really, CR is the clock rate. So, and the CPI is the instruction count. So the CPI is cycles per instruction. Cycles per instruction. Okay, so let's look back at that. And where were we? Oh, yeah, here we calculate. Oh, we already did this. We said the IC instruction count, 1,000,000 divided by, it took 1 second, equals the MIPS. But we can also say, we did all this, so we don't need to do it again. You can also say, this CPU time is all of this. So then we can cross off, and then we have 1 over CC, and that becomes CR. We did this last time. So this is just copying and pasting what we had before. But we just said the MIPS is this, and it's this. I say, remember, we already did this. Fine. First, let's calculate the CPI according to the formula. So this thing looks very complicated and scary, but it's just saying take a sum. Take a sum of all the things. So it's kind of like a weighted average. It is a weighted average because we want to get the CPI, which is what? The cycles per instruction, the average cycles per instruction. That means we know that some instructions take more and some takes less. First of all, let's start with the bottom one. We know on the old computer, the not machine floating point, it's 2 for every instruction. Every instruction is 2. That's what he told us in the question. Remember that this is not telling me how many. There is no instruction in this old computer. There is no instruction floating point multiplication. All he can do is instruct, and each of them is 2. This 30 means how many of those ones he has to take to get that, to get a floating point instruction. So the average is going to be 2 since they're all 2. But the other one, well, we have to take what?
What's the numbers on the left side of the inside of each parentheses, like
I'm about to
0.1?
explain. I'm just, that's exactly what I was. First I explained this, and now I'm going to explain this. So you just are asking the question that I wanted to answer. So great. 4 is how much this multiplication takes. 6 is how much addition takes. Let's see. Oh, there's the 6. And there's the 20 for division. And there's the 2 for integer operations. Now, what is the 0.70? And what are the other numbers? So let's think about the 0.70.
Percentages of the amount of instruction of those instructions.
We saw the 0.70 over here. 70% of all the instructions in this given program, right, with a given benchmark program, in this program, it was 70%, happened to be 70% integer operations, 10% multiplications, etc. So those percentages have to be brought into the picture. We can't just take the average of all of these instructions. That would be assuming that there's an equal amount of multiplication, addition, division, and int. But there isn't an equal amount. There's a lot less multiplication than there is an integer operation. There's more addition, and there's tiny amount of division. So we have to do what's called a weighted average. We're going to take an average, but it's an average based on on the weights that these operations have in this particular program. So that gives us a average CPI of 3.7. 3.7 would be the average instruction in this program took 3.7 cycles, whereas the average instruction in this program took 2 cycles. So you could say, which computer runs faster? Well, he can do all of his instructions in 2. He has to take 3.7 on average to do his instructions. So he's worse. But of course, that's not true. He's not worse. He's better. But we'll have to see how much better. But how can it be that he's better even though it's worse? Because these instructions, it's true that it takes him longer to do these instructions, but some of them are very powerful. He can get a whole floating point multiplication done over here. Whereas this little 2 that he's doing for every instruction, he might have to do a whole lot of them to get something done. So let's see. So where are we now? The NFP computer only does integer operations which take 2 cycles. So what is this 27? Well, we said that there are 100. That's the speed of it. Notice we just now calculated the CPI, but we're going to do CR divided by CPI to get MIPS. CR divided by CPI. Remember, let's just take the numbers. My physics teacher always told me this, and it's a good thing to remember, which is look at the numbers and say, and give a ballpark estimate. What would you say about how much faster the new computer is than the old computer? Well, it's millions of instructions, or sorry, which one does more MIPS? Which one does more MIPS, in your opinion?
The old one?
The old one, exactly, because in a second, he can do, depending on the speed, but the speed's the same, but he can do more of these short instructions in a second than this guy can do these longer. These takes more cycles to do his instructions. So he can do more millions of instructions per second. So he's got a MIPS that's better than the new computer, even though presumably the new computer is better. So that's an example.
Only for this benchmark though, right?
Only for this benchmark. Yes, it could be other benchmarks that would, right, exactly, only for this benchmark. But we're using a benchmark. In other words, we might use 5 benchmarks and they might all be better, and it might be the 6th one that we didn't use. That was the one that would have shown that the new computer is better. But the main point is that the MIPS is just saying instructions are instructions. All instructions are equal. So I just want to know which one can do more instructions. But that's unfair because not all instructions are created equal. Some instructions get a lot of work done and some get a little work done. So on the new computer, he can do fewer instructions in a second, but those instructions are much more powerful. But let's just continue. So since we have the CPI, we need to calculate the CR to get the MIPS. That's what we're gonna do in the next slide. So the CR, well, we got the CPI, here it is, times 1,000,000. And the CR, well, we were given the CR. It's 100. It's the CR is the clock rate. The clock rate we were given is the constant in the two computers as 100 megahertz. So 100 million cycles per second. And we divide this up and we get 27, which shows us that the old computer, the new computer, the MFP is the new computer, can only do 27 million instructions a second. And the new computer, the old computer, the not floating point, the old one can do 50 million instructions per second. He's much better. Ki'ilu, although it's not really true. He's not much better. But it seems from this measure that he is better. So we have to get a better measurement. So let's keep going. And that's what question 2 is. Given that the old computer, the new computer, it's confusing because the N, I always think it was new, but it's not. The new computer executes, let's say that the new computer did a program. It's like a different question, but well, yeah, it's a different question. It happens to be the same frequencies. But given that the new computer executes a program in 3, you know what, maybe it's, you know what, I'm going to change this from A to V. It is that same program because we never said how many lines it was. We just said percentages, right? We just said that how it does. We just, yeah. Fine. Just checking. Yeah. So it's the same program. So given that the new computer executes the program in 300 million operations, how many integer operations are required by the old computer to execute the same program? So here's what we do. First of all, we take these percentage frequencies and we say, well, it's all got to come up to 300 operations. So, and we know that the frequency, the ratio, we know it's always 10% of the instructions are going to be multiplication on this program. So therefore, of the 300 million, it must be that 10% of them were multiplication, which means 30 million. And similarly, 15% of the 300 were addition, so that means 45. And similarly, division was 5%, which 5% of 300 is 15. So we know that's how many. Now, this is a percentage, a ratio, but this is the actual number of division operations in this program that it had to do. And how many integer operations? 70%. Well, 70% of 300 is 210. So that altogether is going to come to our total of 300. Now, once we have these numbers, we know that the NFP, not the old computer, had to do the same program. So he also he had to do 30 million multiplication of floating points. But every of those 30 million that he did, in order to do them, according to that table we had before, it took him 30 into operations. Remember that table? That was what that's why we got that table there. By the way, this is all very easy because my physics teacher in high school would throw in extraneous data just so that you couldn't figure out which based on which data he gave you. In other words, we don't, for some reason, in Machon Lev, nobody figured this thing out, but that you should just throw in extra data and confuse the students to make sure that they know what they're doing. But here, we can basically say, well, wait a second, we never used this piece of information yet. Clearly, if he gave it to us, we're going to use it. So let's use it. So this 30 tells us how many multiplications, how many int operations we have to do for every multiplication. So we're going to use that down here. And we say 30 operations for every multiplication. So if we got 30 multiplications, 30 times 30 is 900. So too, how many, for every addition, we need to do 20 operations. So that's going to be 20 times 45, 900. And 50 for division. So of those, we only had 15 million, but we have to multiply them by 50. That's how many int operations. So in the end, we're going to have 2,700. And now, for this is the last one, the integer operations, it's going to be obviously 1. Every integer operation remains an integer operation. So that remains the same.
And to calculate the cycles, you just multiply everything by 2?
Yes, if you want to calculate the cycles, yes, you multiply everything by 2.
What is it?
Is that on both? Is that for both computers or just the NML?
No. Over here, it's 2. But over here, it's not 2. Over here, we got a table of how many, for a multiplication on the new computer takes 4. And remember, and Yitzchak said, how come it's 6 for addition? And I said, that's because that's what it is. I don't know why. That's the 6. We got to multiply the 6 still. We got to multiply the 4 here, and the 6 here, and the 20 here, whatever it was. I don't remember exactly what it was. But so therefore we got all these numbers. This is how many, the number of operations, we're not cycles yet. Number of operations here and number of operations here. So actually he did a lot more operations. He did how many more? 10 times more, almost. And ballpark figures,
But they weren't
10
as
times
useful
more.
operations, correct?
What?
But they weren't as useful operations.
Exactly, they weren't as useful operations. And that's
What
what
does
we're
it
going to
mean, the
see.
amount of operations on the emulator on the previous slide?
What? Well, that's what we're going to do right here. In this next slide, we are going to see exactly how useful it was. We're going to get what is
No,
the
but
program.
what does that column mean on the previous slide?
What is this
Amount
column?
of operations? No, the one to the left of it.
This?
Yeah.
Amount of operations on the emulator. In other words, well, maybe it's said badly. Amount of operations in order to emulate.
That's like how many times you use the multiplication like command.
No.
How many integers commands you need to do the float command?
It looks like the
Yes,
ratio.
yes,
between
that is correct.
MFP
Yitz
and-
said it correctly. You ever hear it said? Say that again, Yitz.
Yeah, say it again.
The amount of operations needed to do float command through like integer commands.
Exactly. The number of because this is on the old, these two this column is for everybody. This column, this, by the way, this frequency is in the high level program. Because this frequency only makes sense in the high level program. Because in the low level program, in the machine language, there is no floating point addition in this computer, in the old computer. He doesn't have it. It would be meaning this chart only makes sense in a high level language. And that's why we emphasized before that when you're measuring in million flops per million floating point operations a second, we always look at the high level language, because this values are meaningless in the old computer. Because if I look at the assembly of the old computer, I wouldn't see a single thing related to floating points. I would just see int operation, int after int operation. And that's what we mean by emulation.
But the compiler,
Because in order to get this done, in order to get this multiplication done, he has to achieve the result of floating point operations by using lots and lots of integer operations. How many lots? 30. For division, 50.
Okay, thanks.
So that's what caused him to be slower, even though he's got a lot of operations. Okay, so now that we have those numbers, basically what we have to do is just take this grand total. Well, let's see what we do. Okay. Basically, we're doing that same thing we did before again. Look at that. It's 30 million times 4. Well, that's what we just did. Y4. Y4. Wait a second. Right. Let's start on the right side. This is how many 210 is what? Is how many integer operations he had to do. 210 million, because it was 70%. And each of those took 2 cycles. This is the new computer. That's the floating point one. Because we can't just compare, let me go back. We can't just compare this and say, oh, he's 30 million, he's 10 times better. He's not 10, he does it in much fewer operations. Yes, that's true, he does it in fewer operations. He does it in more operations. But that's not the whole story, because some of his operations are slow. This is not number of cycles. This is number of operations. And some of these operations may take very long. So we have to throw that in and make this 30 larger, and then we'll compare apples to apples. So that's what we're doing here. We're saying, take these 210 that are of type add, and they each take 2. But take the division ones, there are 15 million of them, they take 20 cycles. Take the addition ones, which are 45 million of them, and they take 6 cycles. And take the multiplication operations, they take 4 cycles each, and there are 30 of them. Now I've got the number of cycles. That's the cycles. That's all the cycles. That's the sum of the CPI. Let's understand this thing here. The CPI of that command and the number of cycles. The CPI is the cycles per instruction. That's this 2 cycles per instruction. That's this 20. 20 cycles to do a division. Cycles per instruction times the count. Times the instruction count, the IC, the instruction count of that type. Well, the instruction count is 15 million of division. So 15 million times that. This is the sum of all of those. But the sum of all of those times the CC. What is the CC? Not the CR, the CC. That's how long, that's a time. It's very confusing. The CC is a time. That's how long a cycle lasts. The cycle length. What is the cycle length? Well, if it's a 100 megahertz computer, as we was given in the question, then it means it's 100th of a millionth. And it's 100 millionth of a second. So that's why I divide it here. This is times 10 to the minus 8. 10 to the minus 8 is the same thing as dividing it by 100 million. And that gives me 11.1 seconds. Now, this is kind of dumb, the way you did this.
Why are we dividing it by 100 million?
Because that's the 100 millionth of a second is how long each cycle is. We calculated this whole sum is all the cycles that the program took. But I want to know time. I want to know how many seconds it took to run this computer, this program. By the way, it's not the running of the program. It's the running of the math part of the program. There could have been I/O. There could have been writing to disk. We're not counting that. We're just calculating. This is not an actual number that you could measure by running it and putting a stopwatch. This is taking out all of the commands and seeing the theoretical running time of them, of just the commands, and excluding all I/O. So anyway, that is 11.1. What did you ask, Isaac? You asked the question.
Wait, so the clock cycle is the 30 in this case, and the What size you stand for again? That's the instruction count.
That's the instruction count. That's how many of them. That's the 45 million. The CPI is how many cycles per instruction. Cycles per instruction. How many cycles it took. So if I take how many instructions there were, there's how many load words were there, and each load word took 6 cycles. So I have let's say there were 45 million times 6 gives me 45 or 90 and 270 million. 270 million cycles. But that's not good enough. I don't want to know cycles. I want to know actual time. So I've got to say, well, how long is a cycle? A cycle is 100 millionth of a second. So I've got to multiply that by 100 millionth. How do I multiply? That's 100 millionth. That's 10 to the minus 8.
That's the CC. That's the clock cycle
That's
part.
the CC. Yes, the actual length of time that the cycle lasts. And that gives me 11. Now, this is a dumb way of doing it because I already had some information that was useful. He forgot that we calculated in the previous question that we already had this, the CPI, the average CPI is, I don't need to, I've already multiplied the 4 by the percentages. So I've got the average. So why can't I just take 3.7, which is the average per instruction, and multiply 3.7 times, instead of multiplying 6 and this, just multiply 3.7 times 300 million, and then divide it by this. Now, if somebody does that on their calculator, well, we could do that.
Why times 300 million?
Because that was given in the equation that was given in the problem that there are 300 million operations. In other words, instead of taking each operation and multiplying it by its length of time, and then taking that's essentially taking a weighted average of all the instructions. But I already took a weighted average in question number 1. So I don't need to I'm recalculating something I already calculated. I already multiplied 30 times 4 and 45 times 6 over, where did I do it? Well, here, 10 times 4. Remember 10, why was it 30 times 4? Because it's 10% of 300. So this is the percentages. This is a weighted average. That's like the average CPI for the new computer. So I can just take the average CPI and multiply it by the total number of cycles, which I already calculated here as 300 million, and I get 300 million. Here, let me share my screen for a second. You guys got to go. Anyway, try it on your own.
Using the average, isn't it less precise?
What?
If we're using
Exactly
the average.
the same. No,
That's
exactly the same.
Okay.
Exactly the same.
I had a quick question about.
I mean, the 3.7. The
doing.
3.7 might have been incorrect because that might have been rounded. You're right. It might not. I mean, I'm doing it again, but as long as the numbers are meduyak, as long as the numbers are exact, as long as that 3.7 was right, then I should get the same thing here.
I just did 3.7 on my calculator and I got 11.1.
Okay, very good.
I had a question about the homework, like what we were speaking about at the beginning of class.
Wait, let me wait just a second
Okay,
before
fine.
you.
I just
I'll
wanna
let you
get a
finish that. But let me just
question
finish the
before
slide because I have 30 seconds. I don't really have 30 seconds, but let me just do the last part of the slide. And then I said, what is this? This is the CPU time, 11 seconds. Now I said, remember that the CPI of the old computer is 2. So I can again go and take the 260, remember 2,760 instructions, million instructions, times 2, because each one takes 2 cycles, divided by 100 million, and I get 55 seconds. So now I see, when I talk about seconds, that I have 55 seconds and 11 seconds. The new computer is faster. Okay. Oh, here. Oh, this I can delete. Now your question.
Yeah. In the beginning, you were talking about what opcode we should use for this made-up command that we have to make in question 2.
Yeah.
And I think you said that we can just use any that's not already used. but that doesn't make sense to me because like I thought in opcode each specific bit goes to a specific control line.
Yes.
And so the opcode that we choose needs to make sense according to what lines we want on and what lines we want off, correct?
Yes. But I do not think, yes, you are right. But I do not think that the question requires you to redesign the controller. If you're going to add a new line, if you're going to add a new line coming out of the controller, we are then going to have to generate that line and not generate it on every other command. In order to guarantee that this new control line that you come out, that let's say you want it to be 1 for your command and 0 for every other command. So now the controller is going to have to worry and guarantee that it's 0 for every other command. So that means you're going to have to rebuild the controller correctly. And I don't think the question, in other words, and make sure that that line really works and make sure that you took the right one. You're right. So but
otherwise, what we should do is we should.
But I don't think that the question. I mean, I'm not looking for that in the question. First of all, I'm not checking your questions as a Bodec. I'm checking all the questions for all the different sections. So, but my understanding is that you are not being asked in this question to redesign the controller, which you
we
would.
Should choose an opcode that will work with the controller.
If you can do that, then you're very clever. In other words, that's called redesigning it. That's called figuring out which line I can add and then how I'm going to add it. You know what I mean?
No, I'm saying I wouldn't add any line. I would just give it a command.
But you have to add a line. You have to add a line coming out of the controller. Even if you don't add a line coming in, you're adding a line coming out. That line has to come out to be 1 always for your command and for every other command to be 0.
Well, there's like 6 or 7 lines coming out of the controller, correct?
Yeah, but you're going to add another line.
And now they're going to be like 8.
Well, for your new command, presumably you're going to add at least 1 line, I presume.
But doesn't that mean that we are redesigning the controller, which you just said not to do?
Yeah. What I mean to say is you can treat it as a black box. Remember.
Okay, we'll just draw a line on the outside, pretend that we've done something on the inside that will assure that when we get this command, it will put a 1 for that, and for any other command, it'll do what it used to do.
It'll put a 0 on that line.
And it'll put a 0 on that line, obviously.
Yeah, that's right. I mean, if the question would say, it'd be great to have a question that would say, part B, what is the inner workings? In other words, but remember, when we added in our examples, we added like a shift left, 20. We didn't design the logic of that.
So when we choose
should,
the opcode, what should we?
So that's what I'm saying. You can just pick any because it's going to be wrong. Whatever one you pick, it'll be wrong, really.
Okay, fine.
The chances that you would guess you choose one that might work in a simple way, maybe you'll guess that. Maybe
well, I mean, if I need an opcode,
sorry.
Oh, sorry, you go, Amite.
When I read the question, basically the made-up command is very similar to the add command. Can we just then use the add command opcode?
Well, no, we would need to change
but
it.
But the opcode is different. No, you can't, because then it's going to do add. You can never reuse an opcode. The opcodes are designed to do one thing and one thing only.
So, but based on what this command is doing, if we say, okay, so it needs to access 2 registers and it needs to write to memory, there's a specific line for each of those things. So we can just turn it on for each of those things, right?
Yes, we can say. If you need to, let's say you don't need to add any lines. Theoretically, you don't need to add any lines. You can just say, when the opcode is my new number, 33. When the opcode is 33, then I want on the ALU this, and on this one this, and then if everything works, then you've solved the problem.
Yeah, it seems like we can solve it without adding anything, basically, because it's just an add.
Right.
It's
you probably
add to
can.
memory.
You probably can.
To
you
an
probably
address.
can. So if you think about what you're doing, if you think about what the question is asking on a deeper level, what you're actually asking me saying, in order for this command to be supported, first of all, on the multi-cycle, you're right. You're probably going to add less stuff because that's the whole point. You got 5 cycles to do things in. Remember, never change the first 2 cycles. The first 2 cycles are fixed in stone. Don't say you're changing them. You can't. The first 2 cycles are fixed in stone, but you've got 3 cycles after that to work with. You could probably, with the given hardware, get everything done without having to add much or anything.
This is talking about a single cycle configuration.
Oh, it is? Are you sure? I mean, okay, I don't know which.
Relate to the single cycle configuration.
Okay, so then it's single cycle, fine. So then you're going to have to probably add hardware. But if you don't think you do, then maybe you don't have to. But I think you do. In general, you're going to have to add hardware in the single cycle because everything is being used. Anyway, what was I saying? So, I'm sorry. I was thinking the whole time in multi-cycle. Doesn't matter. Or I was in the middle of saying something. Well, whatever. Yeah. Anyway, you'll add your new command. You'll say what. That's what I was saying. I was saying by specifying what the new command, what the controller is going to have to put on its outlines. By doing that, you're essentially giving instructions to the engineer. You're giving the design requirements of the controller. You're saying, I need the controller to have logic gates inside it such that when this opcode comes in, it produces these and these outputs in addition to what it did before. So you're designing, you're giving the design requirements. It's not the actual specification of how to do it, just the requirements. See what I'm saying? It is the first step in rebuilding. First you give the requirements, and then you go and say, okay, now that I got these requirements, I can hand it off to somebody else, and he knows what he has to do. He just has to make sure that when this number comes in, these lines get lit up.
Okay. Fine.
All right. So guys, take a look at the video that I put up about Booth, and give me comments.
Okay, thank you.
All right.
Sure.
Thank you very much.
Sure. Take care.
You too.